Hello everyone, we are Team Semi Genius from University Putra Malaysia. We'd like to present our design and findings on greening the petrochemical industry, specifically greening the naphtha steam cracking process for ethylene production by utilizing hydrogen or the electrical energy. These are the 5 members behind this wonderful project. Steam cracking is a crucial process in which a saturated hydrocarbon with the naphtha is broken into smaller or unsaturated hydrocarbons before the production of ethylene. Conventionally, the fuel used to heat the naphtha is natural gas. There are major issues associated with the conventional naphtha steam cracker. Steam cracking consumes more than half of the total energy in ethylene production, and the energy corresponds to 70% of production costs. This process is also responsible for 180 to 220 million tons of carbon dioxide emissions worldwide. To resolve these potential issues, alternative energy sources such as hydrogen and electricity can be considered. The main factor for hydrogen utilization is hydrogen production itself. There are several ways to produce hydrogen, including alkaline water electrolysis, steam methane reforming, and biomass gasification. And among these methods, we think electrolysis can be considered a potential source of hydrogen as it produces green hydrogen, which is a type of hydrogen that has the least contribution to CO2 emission. Next, electricity can also be used to generate heat energy instead of relying on the combustion of fuels. Electrification of furnaces is estimated to reduce up to 95% of carbon emissions. Now, the process flow diagrams. The image shows the PFT for the base case development, which uses the natural gas as fuel. The following PFT shows the hydrogen generation and also the hydrogen-based furnace, which involves approximately 15 unit operations, including 1 electrolyzer.
Right now, I'll be explaining the concept of the simulation. In terms of a software, we use Aspen HYSYS and Aspen EDR. We use Aspen HYSYS for the process simulation of the furnace cracking, and added with the Aspen EDR for the details design of the furnace. Before we start the simulation, let's have a look on the pre-setup. So for the fluid package, we choose Penn Robinson, and it is widely used in the petroleum cracking industry. And we use electrolyte fluid package for the hydrogen production part. Actually, the main reason why we choose HYSYS is because of the feature of petroleum assay, which we could input a naphtha TPP curve and naphtha feed property to generate the naphtha feed composition, as shown in the right figure. So overall, for whole design, we follow the guideline from the booklet, including the feed amount needed, the product ratio, and the outlet steam condition. A few assumptions has been met to ease the simulation, including the steady state operation, no significant pressure drop, and negligible heat loss. This is an overview of the base case cracking simulation. The main unit operation including the fire heater here, which represent the furnace condition, the separator to represent the steam drum, heat exchanger to represent the transfer line exchanger, and also delay cooker to represent the cracking reaction. The reason we use the delay cooker here, right, is because of the fire heater wouldn't really undergo the reaction in the HYSYS. So we use the external reactor unit op here to demonstrate the endothermic reaction and composition changing due to cracking. So all in all, we simulate the process and ensure it is within the range of the condition. At the same time, we do the details design of the furnace using Aspen EDR. We design the convection part, the radiation part. We also design the firebox, tube details, bank arrangement, tube sizing, material use, and so on and so forth. This all the design is to ensure the heat transfer will work effectively, reach the desired condition, and at the same time close to the reality without the simulation error. The whole same concept could be used in the hydrogen-based cracking simulation. Just that in this simulation, we include the hydrogen production part, which will be explained by my teammate later on.
Next, for the simulation of hydrogen production via alkaline water electrolysis. The electrolyzer or stack is replaced with a conversion reactor for simulation purposes. The parameters of the system are then optimized to get the desired amount of hydrogen for naphtha steam cracking. In the simulation, the green colored region indicates the cathode, the electrode where hydrogen will be produced, and the blue colored region indicates the anode. The feed consists of 62.49 weight% of water and 37.51 weight% of KOH. The hydrogen purity obtained for this system is 99.95%, and the amount of hydrogen produced is 1014 kg per hour. Based on the power required for hydrogen production, the features of the electrolyzer can be estimated as shown.
Thank you, Saravanan. So in terms of the electricity-based cracking simulation, we doesn't really undergo the high-C simulation. But it's more on that we consider all the electricities are coming from the solar panel. Then we use the heat duty from the base case simulation together with the feed-in tariff of solar system in Malaysia to find out the total amount of the electricity usage of this cracking method. So for the further explanation will be done by my teammate later on.
Next, I will present the data overview for different technologies in terms of their energy consumption, direct and indirect GHG emissions, specifically for CO2 emission and the efficiency. As you can see in this slide, the most highlighted point is hydrogen-based technology have the highest energy consumption in furnace cracking, where the electricity base has the lowest energy consumption in furnace cracking. Therefore, we can see the percentage improvement of electric base is positive value, which indicates there is improvement on electric base compared to natural gas-based case. Meanwhile, hydrogen-based case show negative value indicates a decrease in percentage improvement. However, we believe hydrogen-based technology have higher value of energy consumption due to heat transfer in H2 combustions. Next, in this slide shows that natural gas contributes to direct CO2 emission, meanwhile, hydrogen and electricity contributes in indirect CO2 emission. Furthermore, we can see electricity contributes much lower indirect CO2 emission compared to hydrogen-based. For furnace efficiency, the efficiency for electricity-based technology is higher than hydrogen-based technology. Electricity-based case furnace directly convert electricity into heat through resistive heating elements or induction heating, which can achieve relative high conversion efficiency. Meanwhile, in hydrogen-based, it involves hydrogen production, which it leads to some energy losses. There are some potential operational challenges of hydrogen-based furnace, which are hydrogen is highly flammable gas, which need to be more careful while operating. Besides, hydrogen-based furnace need to maintain uniform heat distribution to achieve consistent cracking. And lastly, the purity of hydrogen need to maintain as it can affect the cracking process. For the equipment requirement for H2 base, which include hydrogen supply system, hydrocarbon feed system, furnace, and its hydrogen burners. Next, there are some potential operational challenges of electricity-based furnace, which are due to limited source in internet related to electricity furnace. Electric resistance might not be able scalable for these large-scale processes. It also can be costly. And lastly, the furnace cracker is heavily dependent on a stable and reliable electricity supply. For the equipment requirement for electricity base, which include solar panel, electric heating elements, electrical infrastructure, and the furnace. For the potential improvement for conventional technology, include the emission reduction that invest in emission control technologies and implement the carbon capture and utilization technologies. For H2 base, can be more focused on optimize the hydrogen and storage supplies using advanced H2 storage technologies to increase storage capacity and efficiency. Last but not least, for the electricity base, more focus on optimize the energy consumption of the electric heating elements to reduce operational costs and minimize environmental impact. Then I will pass to the next presenter.
Next, I will continue with the market analysis for both electricity and hydrogen-based cracking furnace. Solar power is practical to be the electricity source for electrified cracker due to the abundant sunshine. It's a big potential of using PV system as renewable source for electrified cracker as it's a cutting-edge technology. If we're using this technology, there's fewer competition in the market and therefore offering considerable long-term business potential. There are 3 companies which are Linde, BAS, and Sabic team up to develop an electricity cracking furnace by using renewable source. The solar power source for our project is come from Koramaraang Solar Park in Terengganu, Malaysia, as it's able to produce 116 megawatt electricity and reduce up to 170,000 tons of carbon footprint. For hydrogen-based cracking furnace, in line with SDG 7, utilization of clean energy has very high demand among the petrochemical industry players. Therefore, most of the companies turn to invest in clean energy such as hydrogen gas to reduce GHG emissions. One of the companies which utilize the hydrogen-based cracking furnace is INNOSIM, which has raised Europe 3.5 billion to build the hydrogen-based cracker in Europe. Move on to the sustainability of plant design. It can be classified into 3, which are feasibility view, economy view, and IAE. Since the feasibility view has been covered by Ardeanna, I will continue to explain in terms of economy view. If compare the utility expenses for 3 cases, the utility expenses for hydrogen-based cracking furnace is higher than electricity cracking furnace. The electricity cracking furnace has higher economy sustainability as is cost effective. If compared between the electricity cracking furnace by using renewable and non-renewable energy sources, even though the price of tariff based on TNB is much more cheaper than renewable source, but in order to promote sustainability, the green technology of using solar power is preferable. From the aspect of general costing, the total costing for hydrogen-based cracking is the highest, followed by base cracking furnace and electricity cracking furnace.
I'm delighted to continue the presentation by presenting to you today an environmental impact assessment for 3 different technologies used in the naphtha cracking processes, which are conventional method, hydrogen-based cracking, and electricity-based cracking for steam cracking furnaces. For the conventional technology, direct emission includes sulfur dioxide, nitrogen oxide, carbon dioxide, particulate matter originating from fossil fuel combustion. Additionally, indirect emission are associated with fuel extraction, transportation, and refining processes. Unfortunately, this method has limited potential in reducing the industry carbon footprint due to its high direct and indirect emission. Moving on to the hydrogen-based technology, direct emissions are minimal or negligible. Hydrogen production through electrolysis results in only water vapor as a byproduct. However, the crucial aspect lies in the indirect emission, which depends on the electricity source used to power the electrolyzer. For this method to be truly sustainable, it requires green hydrogen production aligned with the low carbon electricity generation. Lastly, we have the electricity-based technology. Here, direct emissions are virtually non-existent as solar panels convert sunlight into electricity without any combustion, leading to a reduction in greenhouse gas emission. However, there are some indirect emissions linked to solar panel manufacturing, transportation, recycling, and disposal. Yet, with responsible practices, this technology offers substantial potential in reducing the carbon footprint of ethylene production. Moving on to the sustainable plant design and green design, first and foremost, optimizing the design for ease of construction, efficient resource use, and reduced construction time is important. A well-planned layout and modular design can streamline construction and commissioning processes, minimizing disruption and maximizing efficiency. Constructability plays an important role in sustainability. By focusing and optimizing resource utilization, including raw material, water, and energy, we can significantly reduce waste generation and enhance resource efficiency. Safety is of utmost importance. By incorporating state-of-the-art safety features, conducting hazard analysis, and performing risk assessment are important steps to identify and mitigate potential safety risks, ensuring the well-being of the plant and personnel. But sustainability doesn't end with construction. We must consider the entire life cycle of a plant, from its inception to decommissioning. Conducting a comprehensive life cycle analysis allows us to evaluate the environmental and economic impact at each stage, presenting opportunity for continuous improvement. By adopting these sustainable practices, you can pave the way for a greener and a more efficient plant design. Based on the comprehensive evaluation, we are blessed to present our recommendation. At this stage, the best choice for e-crack is hydrogen-based cracking technology. Allow me to elaborate on the reason behind this decision. Both technologies offer one crucial advantage, which is zero direct greenhouse gas emission during the ethylene production process. Firstly, hydrogen-based cracking provides practical integration with minimal design changes, ensuring a smooth transition into our current operation without causing significant disruption. Secondly, this technology offers immediate flexibility. Implementing hydrogen-based cracking can promptly reduce our environmental impact. On the other hand, electricity-based cracking has the potential for greater sustainability. When powered by renewable energy, it becomes an even greener option than hydrogen-based cracking. In conclusion, we recommend taking immediate action by implementing hydrogen-based cracking, benefiting from its practicability and immediate environmental impact. Simultaneously, we urge exploring electricity-based cracking for greener and a more sustainable future, embracing its potential benefit and long-term positive impact. In conclusion, the evaluation of hydrogen-based and electricity-based cracking technology presents promising opportunity for a more sustainable future in ethylene production. This alternative offers the potential to significantly reduce greenhouse gas emissions compared to conventional naphtha cracker. By embracing innovative solutions like e-crack technology, the petrochemical industry can take a significant step toward mitigating its environmental impacts and contributing to the global effect of achieving sustainable development goals, particularly SDG 7, objective of providing affordable, reliable energy for all. Before we wrap up, we want to express our gratitude. Special thanks to INNOSIM 2023, your platform provided us with a valuable learning experience and network opportunities. We are also thankful to Dr. Mohamad Rezi and Encik Muhammad Hassan for their guidance in completing this process simulation. For more information, please refer to our reference material, scan the QR code, and click the link provided. Lastly, thank you for being a part of this journey. Goodbye.